Question 2 basically asks us to find the derivative two different ways and make sure that they're the same. So here's actually question 1, but it's the second question on the exam. They're parametric equations, and we have x is equal to t squared and y is equal to t cubed. So if we use the theorem in the book, we get dy dx is just we take the derivative with respect to t of both of these and form the quotient. Let me write that down here, dy dx. And we could pretty much read that right off, right? So dy there is 3t squared, and dx is 2t. And we can simplify this dy dx, pretty nice, is 3 halves t. Now, if I go about this by solving, let's say, this for t, we'd have t is equal to the square root of x. Substitute it into y, we'll put it back into standard f of x equals y notation or style. So this is equal to the square root of x cubed. So y is equal to x raised to the power of 3 halves. And the sort of standard here, I'll write it like dy dx is equal to 3 halves x raised to the power of 1 half. Now they look different, but watch out. Remember, this is the slope of a tangent line at a point on the curve, but it's as a function of t, the parameter. Here is a function of x. So to compare these, we either have to substitute in, we have to write t as a function of x and make a substitution there, or x as a function of t and make a substitution there. Well, straight away here, I guess I've got x is equal to t squared, so let's go ahead and do that. And we get dy over dx equals 3 halves. Well, t squared and raised to the power of 1 half is just t. So check. So there's that one. And then there's a second one. And again, I mean, if those two aren't the same, then something's wrong with our mathematics. Either the way we're doing it or in the theory itself. But the theory itself is, I think, well enough established. I don't think we're going to be doubting that. But you're welcome to do it if you want. Let's see, this part B here. Part B is x equals the natural logarithm of 5t, and y is equal to natural logarithm of t squared. I think we could probably, again, almost read this right off if we use the theorem in the book, which is really what we want to do. The derivative of this, hey, just a quick note on this right here. You can write this like 2 times the natural logarithm of t. Your call. That's the rule of exponents. And that'll make taking the derivative a whole lot easier, because what's the derivative of this? That's just a constant. What's the derivative of the natural logarithm of t? It's 1 over t. So that'll be 2 over t. 2 over t divided by, what's the derivative of this? Well, it'll be 1 over 5t times 5. Think about it for a second. Look at that right there. The derivative will be 1 over 5t times the derivative of that, which is 5. So 1 over t. So 1 over t, and we get dy dx. We get some nice canceling here, and we get, lo and behold, just 2. Now, if on the other hand, if say I solve this right here for t would equal, by the definition of natural logarithm, t is equal to, 5t is equal to e to the power of x. Or you could say exponentiate both sides, whatever terminology you want to use, but it really is straight from the definition of what a logarithm is, right? The bases are. So this raised to this equals that. From that, that's not really visible. Let me write over here. So from this, we get 5t is equal to e to the x. So t is equal to 1/5 e to the x. Let's substitute that in here. How about this one right here? So we'd have y is equal to 2 times the natural logarithm of 1/5 times e to the x. And let's take the derivative of this. Hey, don't make a mistake and cancel that. You can't do that because this 1/5 is in there. At any rate, how do we find the derivative of this? Dy dx. Remember, that's a function of t right there. But dy dx, the constant's out in front. The derivative of the natural logarithm, we use the chain rule. So it's 1 over 1/5 e to the x times the derivative of the inside here, which is 1/5 e to the x. And yeah, you guessed it, that's 2. So check. And that's question 2. Let's see. Now the third question is, let me do that and then that'll end this video here. I'll erase all this stuff. Is to show using algebra and trigonometry something. So here I did specify how you have to do something, as opposed to just using Desmos to make a graph. But we have x equals 1 plus 3 cosine t, and we have y is equal to 2 plus 3 sine of t. And we are asked to show that this is equivalent to a circle. Well, let's just try the obvious approach. We could try something slick or ingenious, but let's just plow ahead and do what we've been doing, which is solve for this parameter t. If I subtract 1 and divide by 3, we would get cosine of t is equal to what? X minus 1, all divided by 3. And so t is equal to cosine inverse of x minus 1 divided by 3. And let's substitute that in here. So we get y is equal to 2 plus 3 sine of cosine inverse of x minus 1 divided by 3. And again, for the umpteenth time, like I said, sooner or later, you're going to use this so many times, you might as well commit it to memory or know it. We're going to use the Pythagorean identity, and we're going to get 3 times the square root of 1 minus, well, to save me having to write some stuff down, right? It's going to be, well, no, maybe I better write it down. Well, it's going to be 1 minus the cosine of this squared. So the cosine of this squared, the cosine of the cosine inverse cancel each other out, and we get x minus 1 over 3 squared. Now our task is to simplify this. Now we're done with the trig, and let's see if we can simplify this somehow, some way. Maybe it's not obvious exactly what we want to do at first. Let's subtract the 2 and just get that out of the way. Put it over there. And then 3 times the square root of this ungainly looking thing here. Maybe is a little problem off to the side. We can try, see, what can we do with this 1 minus x minus 1 over 3 all squared? Well, let's go ahead and multiply this out. X squared minus 2x plus 1 all divided by 3. Right, this is 3 over 3, common denominator, all that good stuff. It's 3 minus everything in there, right? So what will we have ultimately there? We'll have negative x squared plus 2x. 3 minus 1 is 2. And all that's divided by 3. So inside here we have negative x squared plus 2x plus 2 all divided by 3. I can have a little fun with the square roots if I want. Look, you can factor out a square root of 3 and then do a little cancellation here. So if you allow me to do this, you don't have to allow me to do it, but we get this. Okay, let's square both sides and get rid of all these pesky, annoying square roots. And we get y minus 2 squared equals 3 times negative x squared plus 2x plus 2. And I see completing the squares in our future here, I think. Tell you what, let's multiply this through here, and we'll get y, because I like this, y minus 2 squared equals negative 3x squared plus 6x plus 6. Now, it's really important that I did all the arithmetic right. It sure would be nice if we could factor this. Let's give that a shot. Maybe we can, maybe we can't, but it's worth a little bit of an attempt here. And if not, no problems. We'll do a completing the square maneuver on it. Because I'm not sure whether that's factorable or not. Matter of fact, let's write it like this. Y minus 2 squared plus 3x squared minus 6x minus 6 equals 0. We're going to try to factor that. So there's a little sort of timeout here. Let's see what we've got here. 3x, x. This does not look promising, does it? If I put a 3 and a 2, does that look like it might work here? Let's see. We get 3x squared from that. Here we get a 6 and a 3. Nah, that doesn't look very good. What if we put a 2 here and a 3 here? We get a 9 and a 2. Nah, it doesn't look very good. So we're going to have to do the completing the square with respect to x on this to get it into the form, the standard equation of a circle. Okay, so how do we do that? Well, hopefully you recall this. I mean, it is a bunch of algebra, and I've done it probably like 10,000 times, so hopefully I recall. Let's go ahead and get the 6 over on that side, and let's factor out a 3 out of these two right here. So we'll get this. There's a couple of different styles you can do this with here, but there's one. Let me make sure I did that right. I added 6 to both sides. Then I factored a 3 out of that. Now what I want to do is complete the square inside there. I'm doing this fast because you should have done this a whole bunch of times before, but minus 2x. Take this divided by 2, 1, square root 1. I'm going to add 1 and immediately subtract 1 equals 6. And then we get y minus 2 squared plus 3 times. Now what do we have here for these three? We have x minus 1 all squared minus 1 equals 6. And we're just speeding down the highway here. Let's go ahead and multiply all this out. Plus, oh no, 3 times x minus 1 squared minus 3 equals 6. Something is not looking right here. I'm going to have to go back and figure out what that is. But plus, because this is looking sure enough like an ellipse, but not like a circle. But let's see. Hey, let's add 3 to both sides, 9. And that 3 is the bothersome number right there. Of course, that's fine. Look, if that 3 wasn't there, we'd have a circle, right, with radius 3. So I tell you what, I don't really feel like redoing this whole video. Let's just chalk it up to a careless mistake. See if you can find it. If you can't, I'll do it in class. I must have made some sort of a silly mistake. I don't want this video to go too long, and my computer dumps the whole video. Let me see if I can quickly find the mistake somewhere. Oh, where did I start off with? We did this. X minus 3, we square it, square that. That looks good. There was a minus sign there. Oh, there's a lot of work that went on there. Oh, I already erased a lot of in between stuff. There was a 3 down below. Hey, this move right here. It's fine. It's not a mistake. I just wanted to show you this maneuver right here. This little portion right here. We had 3 times the square root of 1 minus x squared minus 2x plus 1 all over 3. That's 3 squared. So the common denominator is 3, right? So you'd have 3 minus x squared plus 2x minus 1 all over 3. And that's 3 times the square root of 3 minus 1 is 2. Plus 2x, I'll write it like this, minus x squared all over 3. That's 3 over root 3. If I factor the 3 out, times the square root of 2 plus 2x minus x squared. And that's root 3 times the square root of 2 plus 2x minus x squared. Funny, that looks kind of factor, but that is basically, I think, is that what I had? Oh, there was the mistake. You can go back and trace it through. I had, oh no, that we squared both sides. Okay, we squared both sides and we got this. Square root of 3 squared is this. There, that's squared. We left that alone. I'm just checking for signs and everything like that. Okay, multiply this out. We get this. I factored a 3 out of the first 2. That's fine. Nothing wrong with that. Added a 6 over this side. Geez, I don't know. Oh, did I say this is a circle? Uh-oh. I don't know. Hey, well, let's do this one in class. I'll tell you what, I'll finish up. I made a silly mistake in there somehow. I don't know where it is. I'm getting the equation of ellipse, not a circle. And by looking at it, this should be a circle. The way you can tell is same parameter there, and those both have a 3 in front. And if you think about it, if we get rid of that, that's what we're really graphing. And the 1 and the 2 just give us a shift, wherever we're at. This would induce a vertical shift, and that would induce a horizontal shift, right? Because say x is equal to that, but then add 1. So you'd shift over 1 to the right for a given value of t. And then this, you would calculate that and shift up 2 for a given value of t, your value of y would be shifted up 2. So if we graph this, that's what we're really graphing. And then we just merely added that onto it. So hey, I'm going to end this here, and I'll do this one class. Hopefully you remind me to do it in class.